So this is Math 2413, day 26. Up until now, we talked about indefinite integrals and their basic structure, and this is what it finds for us. The difference between an indefinite and definite is an indefinite integral, you end up with a function with an arbitrary constant back there. Now, the difference between that's an indefinite and we know it's indefinite because there are no bounds of integration, as opposed to a definite integral where you do have bounds. And once we find the integral, then we're bounded by the second minus the first. And this is how they relate. So basically, we have the plus c's, but because they're supposed to end up with a number, a definite number, those plus c's get washed out and fall into place at the very end. All right, so let's look at the processes here. The method we're going to use to start solving these is by substitution using the chain rule backwards. Have we done any of these examples before? Integration?
We've done some integration examples.
So we're used to the formula already. The integral of yes, okay. Yes. Okay, now what this is saying here is this, that the derivative of a function is that. So it means the integral of this one, this is the circle it goes to. The derivative of this function is the integral of that one. Because remember, whenever you take the integral of something, this is actually the first derivative. So this is what the formula will be using. We'll be using this formula pretty much out in there. That's if we can get it into that form. Will it always be that way? No. So what we have to look for here in our substitution method, with the substitution method, you have to find the u variable and the du. So what we're looking here is which one of these would be the u, which is the derivative of u. Well, if we look at this one here, u to the third plus x, or x to the third plus x, the derivative of that one is 3x squared plus 1, which is what this is. So we know this is going to be u, and this is our du. And typically, this is a rule of thumb that the u has to be within some other type of function. What we're looking for here is this. This u function has to be inside somewhere. Since it's to the fifth power, it's a good chance that this is your u and that's your du. The reason this is easier, scratch paper. The reason this method is easier we have the integral of x cubed plus x to the fifth, 3x squared plus 1 dx. Now, because we don't have a rule per se on how to integrate this one. So what we do is once we define our u and du, all we have to do now, then this is u, it's u to the fifth du. So all we have to do is integrate this function. That one's going to be add one on top and add one on the bottom, plus your constant. So once you get this function, then we replace, since u is x cubed plus x, we know that this is our integral, our indefinite integral. So it's because we deal with a much smaller equation, there's not much moving around. However, if we did this one, then we'd have a lot more writing to do. All right, so look at example 2. So the integral of the square root of 2x plus 1. The first thing you do is, since there's only one operation, this has got to be our u. So we have to find du. So this equation is written because the square root, remember the nth root, whatever the root is, goes on the bottom. So it's a square root, so it goes on the bottom. Now, du is supposed to be 2. This is 2u, since you're taking with respect to x, it's 2 dx. All we have is a dx. We're missing the 2. So we have to put the 2 in there to match that. Since we put a 2 here, we have to get rid of it. Cancel it by putting a 1/2 out in front. Now we can go ahead and integrate this one, since we had the 2u du dx, which is dx there. All right, so the integral of 2u to the 1/2, or u to the 1/2, is u to the 1/2 plus 1 over 1/2 plus 1. Plus c. So 1/2. This is 2 over 2, so it's 3 over 2. 3 over 2. So this one, I put it out in front as 2 over 3. Twos cancel, so I'm left with 1/3 u to the power 2/3 plus c. And u was 2x plus 1. Oh, so it's 3 over 2. See, so it makes it much easier to get rid of all this other extra stuff we don't need. If we substitute it down to u, then it's much easier. It's a much simpler process. All right, let's look at the next page. Talk about. Here's a general rule that we're following. Substitution rule. If u equals g of x is a differentiable function whose range is the interval of I and f is a continuous on I itself, then this is what we just did when we transformed it. Because but remember earlier we had f of u du. Well, u is actually g of x, so it's f of g of x, and du would be g prime. So this is f of u du. And that's what we're saying here. So the primary challenge is deciding which expression involving x to substitute. That's the hardest part. So the first thing you have to do is find what the internal function is, the function within the function, the composite ones. Set that equal to u, then find its derivative. This du is that. And then just replace them.
Wait, so you're trying to find the derivative of u of dx or
Yeah, because u is the same thing as g of x. It's
okay.
that internal function. So when you take du is also g prime.
Okay. And then the dx is the
dx
derivative
is the derivative because the function's still with a function of x.
Mhm.
Yeah, so
Okay, so you're using the chain rule.
Yeah, because whenever you take a derivative of u, the derivative of u with respect to x, what it really becomes is du with respect to x dx.
Right, okay.
That's really, but instead of writing all this stuff, we just put du down.
Okay.
Mathematically, we're saying that these cancel each other, but this is what we should be writing, but instead we just put the simpler du.
Okay.
Right?
All
So
right.
now in this example 3, the integral of secant squared 5x plus 1 times 5 dx. Remember, the u part has to be the function that's within another function. So since the outer function is secant squared, this must be my u. When I take a derivative of u, I get 5 dx, which is what this is. This is my du. So what this thing says now is secant squared u du. That's how we wrote this. What I want you all to get used to also, instead of when you look in the cheat sheet, instead of looking for just this type of function, u du equals tangent u plus c, look the other way. See which one has a derivative. See which one has this as the derivative. So you don't always have to look at these integral cheat sheet to find the answer. you can look at the derivatives and see what derivative gives us this answer. So in this one, we see that secant, the integral of secant squared is tangent u plus c. And since u was 5x plus 1 plus c, that's our answer.
Okay, so we're basically just looking at we already know that the derivative of tangent x is secant squared x, so we're just like going back, we're working backwards.
Yeah, so when you look at your cheat sheets, you're not restricted to only one section. So I can't find it, so it doesn't exist. No, now that since we know what this, we can't find the integral of secant squared, let's look for the derivative of tangent. See the derivative ones. So we can use both of these methods to get our answer.
Okay.
I'm trying to show you also that you don't get stuck just looking for one type of procedure.
Mm-hmm.
All right. Example 4. The integral of cosine of 7 theta plus 3 d theta. So it doesn't matter what we have as our dummy variable. It could be theta, it could be t, it could be r, it could be u, it could be anything. So in our equation, remember the innermost, what we're looking for this, f of g of x, g prime of x. That's what we're looking for. So here's the outer one. The f is cosine x. And the g of x is 7 theta plus 3. And the derivative of g is 7. Now, does our equation here satisfy this condition?
Yes.
So, except for there's no 7 here.
So we have to add that.
We have to add a 7. Because we're taking g with respect to theta, so we should have 7 d theta. All we have is d theta. So we put a 7 in front of it. Since we put a 7 there, we have to get rid of it. We have to cancel it out. Because now this is the form we want it to be in. So our answer is 1/7. What's the integral of cosine? So now we have this cosine u du. Yeah, so the integral of cosine is sine u plus c. Substitute it all back in. So u is 7 theta plus 3 plus c. And there's your answer. So again, it's once we transport it from or transform it from cosine 7 theta plus 3 to cosine u, this was a lot easier to look at.
So when we get rid of the du, is that just becoming the c, the plus c, the constant?
Yes, because this is an integral of cosine of u with respect to u. So when we do the integral, that takes care of everything. So then whatever's left becomes the plus c. This becomes the sine u.
You're right, the cosine u. Okay.
All right. Let's look at next Example 5. Sometimes we observe that the power of x appears in an integrand that is one less than the power of x appearing in the argument of a function. We want to integrate. The observation immediately suggests that we try substitution to a higher power of x. So you see here we have our function f, and there's our u, and there's our du. So our u is the exponent, so we have eu. What would du be? If u is x cubed, then du would be 3x squared. Do we have 3x squared? If we have x squared e to the x cubed dx. The function within a function, so the our function u, let's say u, is e to the power u, and u is the function g of x, which is x cubed. So du, or g prime of x, is 3x squared. When we put everything together, f of g of x, g prime of x. So what we should have is e to the x cubed times g prime, which is 3x squared dx. That's what we should have. That's not what we have. What are we missing? We're missing the 3. We have an x squared, we have e to the x cubed. So we have a 3. We put 1/3 in front. So what we had was this, eu du, but we're missing the 3. So the integral of eu is eu plus c. That's why I like the exponential functions, the e's. Again, u was x cubed plus c, and there's our answer. Example 6. Up until now, we've been missing what? We've been doing what? Oh, up until now, we've been missing just a integer, a number. What if we have an extra letter that's not supposed to be there? Well, it's supposed to be there, but there's nothing we know that'll take care of it. Because here's the function f of x, here's g of x. But we don't know what that is. So we know that u is 2x plus 1. So du would be 2 dx. So do we have a 2 out there somewhere? No. We have a 2x plus 1, but we don't have a 2. So we need a 2 there. But what about this x? Right here we have u to the power 1/2. There's du. but we still have this x. Everything else works great. So what we have to do is go back over here and solve for x in terms of u, since that's the only thing we have here is u. So since u equals 2x plus 1, so 2x equals u minus 1 divided by 2. So x is u minus 1 over 2. That goes in this place. U minus 1 over 2. So far, so good? This is a constant. We can take it out in front. So it's 1/2 times that. It's 1/4. So this 2 is moved out in front. So now we just distribute. We have u times u to the 1/2 minus 1 times u to the 1/2 du. So this is 2 over 2, so it becomes u 3 over 2 minus u to the power 1/2 du. So what do we do now? Ready to integrate. What we had on the bottom was 1/4 u to the 3/2 minus u to the 1/2 du. We could split those two up. One fourth. The integral of first one is 3/2 plus 1 over 3/2 plus 1 minus u 1/2 plus 1, and the bottom is 1/2 plus 1. One fourth. This is same as 2 over 2, so it's u to the 5/2 over 5/2. U to the 3/2 over 3/2. Reciprocate those go out in front, so it's 2 over 5 u to the 5 over 2, 2 over 3 u to the 3 over 2. Now if we distribute through there, the 2 and the 4 cancels, the 2 and the 4, so it's 1 over 10 u to the 5/2, 1 over 6 u to the 3/2 over 2 plus c. And then we have to substitute back what we had.
Okay.
What was u? U was 2x plus 1, I believe. Yeah. So it's 2x plus 1 to the 5/2, 2x plus 1 to the 3/2 over 6 And of course, we can simplify these improper exponents. Because 5/2 is 2 1/2. 3/2 is 1 1/2. So what we would end up with is 2x plus 1 squared times 2x plus 1 to the power 1/2. And then 2x plus 1, 2x plus 1 to the power 1/2 over 6. Actually, either of these two answers would work. Actually, any of these three answers would work. It's not too picky.
I've never done a exponent simplification like that before. That's kind of cool.
Yeah, because typically the rule of math, the common conventions of math, if your question starts off with radicals, it has to end with radicals. In other words,
Okay.
you should never end up with rational exponents. But you see a lot of times this book just waives that and just goes ahead and just go ahead and do it that way.
Yeah.
All right, let's look at example 7. Use trig identities to transform integrals. This is what we'll be doing next. Number 7, we're doing these three. Integral of sine squared, cosine squared, and tangent. So A, the integral of sine squared x dx. Because as it says here, sometimes we use trig identities. All right, what's another identity for sine squared? We have a whole bunch of them. Sine squared could be 1 minus cosine squared, but we still have the powers. Or we can convert it to 1 minus cosine the double angle over 2. We have no more exponents, but now we have a coefficient. There's a whole series of them that that's right. You have those in your cheat sheet. The bottom line is we want to get away from the exponents. So we'll use this transformation. 1 minus cosine 2x over 2 dx. This is a constant, so it can go out in front. We can split these up even. The integral of 1 dx is x. The integral of cosine 2x is we're missing a 2, so we need to have a 1/2. Because the derivative of cosine, or derivative of sine, is cosine, times the derivative of this is just 2. So we're missing a 2. So the integral of cosine is sine 2x plus c, which is x over 2 minus sine 2x over 2 plus c. Oh, no, this one has a 2. So this is a 4. Because I forgot this 2 here. So 2 times 2 is 4. All right. Let's look at B. The integral of cosine squared x dx. We have to use the trig identities. Again, cosine squared x is the same thing as 1 minus sine squared x, but we still have a squared, so that's not it. 1 plus sine x over 2. No, it's a double angle. It's 1 plus cosine 2x over 2. One plus cosine 2x over 2. Fraction goes out in front. So we could take the two integrals separately. Oop. The integral of 1 is x. The integral of cosine is sine 2x. We're missing a 2, so it's a 1/2 out here. Plus c. Distribute, we get x over 2. Sine 2x over 4 plus c. The only thing different with the sine and cosine is the first sign. All right, then we do C, which is
Wait, for the last
yes,
one, why was the 2 on the bottom, not the top? For the sine 2x.
because the derivative of cosine 2x, you take the derivative of cosine or whatever, and then take the derivative of the inside. We're missing the 2. So I
Okay.
put 2 there, which give me 1/2, which is where this came from.
Okay, I see.
And the last one is the integral of tangent x du. I think it should be x dx. Yeah, it's going to be x dx. Okay, so what do we know about this? What's the integral of tangent? Well, we could look at is tangent. No, the derivative isn't. Tangent is itself sine over cosine. So if we make this into u, the derivative of cosine is negative sine. So I just need to have a negative there. Because my u is the denominator, cosine. The derivative of it is negative sine. So I just need a negative in there. since I have here tangent is sine over cosine, this is du over u. The integral of du over u is the natural log. So u was cosine x. And that's your answer. Okay, because tangent itself is sine over cosine.
Yeah.
So what we have here is the integral of sine x over cosine x. This is in the form of du over u or dx over x. So yeah, since we're missing a negative sign, that's where that came from. Now we have du over u, which is ln.
Yeah, the cosines is.
Mhm.
So why did we cancel out the second, third one? Second one, where it's just negative.
Because we had to put a negative in front of the sign. So we had to put negative in front to cancel it. Because now tangent x is sine, so this became negative sine x. Well, cosine was u. The derivative is negative sine x. So what I have here is du over u. I substitute it because now it more so than this. This is already in the form du over u, which is the logarithmic function.
Oh, I mean, that, I understand the last one.
Yeah, so it's just that I substituted it from sine and cosine to u du because then it just pops out. It has to be the ln.
Oh.
Okay. Now, you may wonder, this is what I would say here. Okay, now, if you look at the answer sheet that you have, what they did here is a logarithmic equation. Any coefficient becomes an exponent. So this negative is actually a -1 to the exponent, which means this is 1 over 1 over cosine is secant. So you could have done any one of those. But I'd be fat, dumb, and happy if we left it there. It's just that whenever we left it in tangent, they went in secant, cosecant type thing. So, all right, let's look at example 8. An integrand may require some algebraic manipulation before the substitution method can be applied. This example gives two integrals for which we simplify by multiplying the integrand by an algebraic form of equal to 1 before attempting to substitution. So what does that mean? We multiply the integrand by an algebraic form equal to 1. So for example, in this first one, what equals 1? E to the x over e to the x. That equals 1. So if I multiply this integrand, e to the x times e to the x, so I'm just multiplying by 1. So here, what I have now is ex dx. Ex times ex is e2x. E to the x times e to the negative x is e to the 0, which is 1. Okay, so if we look at this equation, this is my u. What would du be? Du would be the derivative of the exponent, which is 2, times the e to the 2x. The 1 goes away. So we're missing a 2. Now we're in the form of du over u, which is ln e to the 2x plus 1 plus c. That's the first one. All right, so what's the next one going to be? This is example 8b. So we have the integral of secant x dx. What do we multiply by here? What's that?
Uh, 1 over secant x.
Remember, we have to multiply it by 1. Right now,
Or by 1.
1 over secant x is not always 1. Not like if last time we had e to the x over e to the x. So we have to get the same fraction on top of each other. So what's the derivative of secant?
Secant tangent. Secant x, tangent x.
So that's our target goal. Because we're looking for the derivative of what that is to get the secant. So let's see what other things equal x, equal 1 with respect to this one. You're right, because secant is 1 over cosine. If we multiplied by cosine over cosine, now we come back to the same thing. We have cosine over cosine squared x. Let's see this. We have cosine over cosine squared. We'll do that. Sine squared x. Yeah, so cosine squared x is 1 plus cosine 2x over 2. So if we have this, we do 2c equals 1 plus cosine 2. No. It looks good, except this is not the du. I need to have sine there. Okay, so what else can we multiply by?
Wait, so if we're aiming for secant tangent, then we need to multiply the equation by 1 that will give us secant tangent, or is that
Well,
right?
this is the derivative. We're trying to find the integral. When we take a derivative, what number would give us secant as the derivative? Is there a trig function that gives us secant as a derivative? Look at your sheet. So look at the derivative section. It says the derivative of this if it equals secant.
I see secant squared, but not secant.
Yeah, we can't have that. Yeah, that's what does it say again? Yeah, yeah, but this is the derivative. This is f prime already. That's going backwards. Let's go in the wrong direction. So this one would stump me. Now what they if the sheet says multiply secant plus tangent. Why secant plus tangent?
Hmm. There's one on here that says the integral of secant HU du equals inverse tangent times the absolute value of sine HU plus C, but I'm not sure what the H is.
Yeah, we can't use that. If that's a hyperbolic, we can't use
Oh,
those.
okay, the hyperbolic.
Okay, so let's see what happens when we do this. If we're multiplying this one, for some reason they chose this. Because they're both functions with cosine on the bottom. So if we had secant times secant x plus tangent x over secant x plus tangent x, we would get secant squared x plus secant tangent over secant x plus tangent x. That's why. The derivative of secant plus tangent. The derivative of secant is secant tangent, isn't it?
Yes.
Derivative of tangent is secant squared x.
Yep.
So the derivative of this equals this. So if u is both of those, then du would be secant tangent plus secant squared. So what we would have here would be du over u. And the integral of du over u is ln u plus c. Oh. And u is secant x plus tangent x plus c.
Okay.
So yeah, the hardest part there is what do you multiply by? I would have never thought about multiplying by this until I saw each of these. This is a sum of those two, and those are the derivatives. Wow, so you do have to try everything. Let's see.
So what was the final answer? It was lnu plus c.
Yeah, ln secant x plus tangent x.
Okay. Yeah, that was a
That was a head scratcher.
kind of problem. Just got to try a bunch of stuff and see what sticks.
And then yeah, is to see what you can multiply to it. But yeah, that one would have taken me a long time to figure out. Oh yes, here. The integrals of the tangent, cotangent, secant, and cosecant functions. The integral of tangent is ln of secant. Integral of cotangent is ln of sine. Secant is ln secant plus tangent. And negative cosecant plus cotangent.
Those are probably good to just memorize.
Yeah, I would memorize because if you memorize, you'll forget. Just have them accessible somewhere.
Okay. I'll put them in the notes app on my phone or something.
Yeah. Okay. Trying different substitutions. The success of substitution depends on finding a substitution that changes the integral that can't be directly solved. Finding the right substitution, as we just figured out, gets a lot easier with practice. If the first try fails, try another one. They always say that. So let's look at example 9. Evaluate this. All right, so since we have a fraction, I put the dz out here. So seeing as the top is 2z, and inside the operation, that's got to be my u. Because when I take du, I get 2z dz. So my substitution is du u to the power 1/3. Because it's a cube root. Just rewrite it. negative 1/3 plus 1, negative 1/3 plus 1, plus C. So that becomes reciprocal, so it's 3/2 and just plug it back in there. 3 cube root of z squared plus 1 squared over 2 plus c. Or you could z squared plus 1 to the power 2/3 plus c. Either one of those will work. All right, that does it for that section. So let's now finish up the course with one more section.